Offshore wind farms have been designed for a fairly long time now. If you count the first solitary wind turbine at Nogersund, Sweden, the construction of offshore wind farms took off in 1990. In 2019, we achieved almost 100,000 times the installed capacity of that first turbine. This clearly shows that we can do this. It also indicates that we have already traveled a long distance through the learning curve, in particular the steep initial part in which great cost reductions are achieved. The Pareto principle, or the 80-20 rule, tells us that we have roughly achieved 80% of effectiveness in offshore wind farm design with 20% of the effort. You can imagine that I'm very happy to have been involved in this in the last 20 years, particularly considering the 20% effort. However, now we enter the era of the 20-80 rule of offshore wind farm design. To obtain the next 20% of performance increase, we'll have to spend 80% of the effort. In this video, I would like to tell you where I think we need to spend this effort. Let me first stir up the hornet's nest with the question about pursuing evolutionary or revolutionary design changes. There is a gradual scale between these extremes, and I'll give you some examples loosely ordered from evolutionary to revolutionary. Changing the power density of turbines, upscaling turbines in farms, changing the drivetrain configuration, making floating turbines, applying vertical axis turbines, and at the most revolutionary example, developing airborne offshore wind energy. The more revolutionary the change, the more the technology is pushed back to the beginning of the learning curve. There could be great potential for such technologies, but they have a lot of catching up to do with the development of conventional technology. The assessment of the potential of new technology suffers almost per definition from a lack of models for both the physics and the performance indicators. It also suffers from a lack of knowledge of the final working design solution, where all teething problems have been solved. We need better assessment processes for technology changes. Nevertheless, for now, we'll have to make educated guesses about which technological changes should be pursued. The more evolutionary these changes, the better these guesses. However, allocation of some no-regrets budget for more revolutionary ideas seems a sensible idea. I nevertheless expect that the groundwork for improvements in offshore wind farm design to concern more gradual changes. This is the realm of what we call rational problem solving, which is an effective approach for complex engineering systems. It relies heavily on good and validated models of the system. In model-based design, numerical optimization plays a big role. Let me therefore start with some challenges of numerical optimization. To let the computer aid the design process, the design problem needs to be formulated very explicitly. This is done by expressing the wishes in objective functions and expressing what is allowed in constraints and expressing the design freedom in design variables. The environment for which the wind farm is designed is expressed in input data. The objective function and constraints are evaluated with models and fed into the optimizer. The optimizer will make changes to the design variables to explore the design options in a smart and efficient way. The models will express the physics of the system, but for instance also the economics, social acceptance and environmental impact. To properly assess the objectives and the constraints, some models require improvements. Think, for instance, of cost models that need to capture the sensitivity of cost to all design changes. Such models are currently often empirical, based on limited data of past technologies. Furthermore, other social values, such as sustainability and security of supply, will become more and more important and will eventually also need to be modeled. For the models that are used, a balance must be found between, for instance, accuracy and computation time. One direction of improvement pursued here is the use of so-called surrogate models. These learn from complex and detailed models and use simple expressions to interpolate and extrapolate model outcomes for other situations. The final challenge I like to mention as regards the numerical optimization is that we'll end up with a lot of models for different disciplines and various options for the optimization algorithm. From these, we'll have to make a selection and make connections to deal with the couplings in the design problem. This is what we call the workflow for optimization. The best matching selection and connections of models and optimizers depends on the designer's needs. This is the domain of MDAO, or Multidisciplinary Design Analysis and Optimization, which needs to be further developed for offshore wind farm design. Finally, I'd like to mention a few issues that further challenge the design exploration. First, we'll have to deal with uncertainty in both data and models. Many external conditions are variable and not completely known. We need to quantify the uncertainty in the assessed performance and use this information in design decisions. This could, for instance, be done by including risk as a separate performance objective, or by making robust designs that are less sensitive to uncertain conditions. Second, there is a practical limitation in the number of design variables that can be used in numerical optimization. The more design variables we use, the more time the optimization takes. This means that some design choices need to be fixed in another way. We can apply knowledge-based engineering principles to capture experience with previous designs. For instance, this can suggest which concepts are best for certain conditions, or it can complete parts of the design automatically. Third, numerical optimization is not a push-button solution that gives the final design solution all at once. We need procedures to address the imperfections in the formulations of the objective function and the constraints, and in the models and optimizers. The numerical optimization is only a proxy of what we really want, and the result is usually not the true optimum solution. This implies that methodologies are needed in which human designers interact effectively with numerical optimizers. Fourth, the wind farm design process needs to be adapted to the dynamic development process in which it is applied. During the development of a wind farm, many changes occur. New data becomes available, some design choices need to be fixed midway, while other design choices drop off, etc. As the design progresses, design choices need to leave sufficient allowance for future changes, but nevertheless converge towards the final solution. Last but not least, wind farm design is a collaborative process with a team and with teams and information, software and other resources divided over different places and stakeholders. Besides the development of computer-aided design support, there is a need for action research to address the participation of humans in this complex collaborative design process. With all these challenges, offshore wind farm design may seem to be a dazzling task. Let me therefore take you back to the beginning. We are perfectly capable of making good wind farm designs. Nevertheless, improvements in computer-aided design and design procedures will help us to make them even better. But these improvements won't come easy anymore. At the same time, developments of more revolutionary design changes will run in parallel and keep us all at the tip of our chairs to see what it will get us. I hope that this outlook makes you as excited about offshore wind farm designs as I am.